In the previous lecture we have derived the Newton's divided difference interpolating polynomial. Let us just write down what is the formula that we have derived there. We call the formula as the Newton's divided difference interpolating polynomial or interpolation polynomial. We have written it as the polynomial f x is equal to f x naught plus x minus x naught into the first forward difference f x naught x 1 plus x minus x naught x minus x 1 into the second forward difference f x naught x 1 x 2 plus so on. We have the products x minus x naught up to x minus x n minus 1 and the divided difference f x naught x 1 x 2 x n. To apply this interpolating polynomial, what we need to construct is the divided difference table, and from the divided difference table we can pick out the values of the first divided difference, the second divided difference and so on, the last divided difference, substitute it, and that gives you, then we can simplify it and get the interpolating polynomial. If we want only the interpolation at a point, we need not simplify it, we can straight away substitute the value of x is equal to some given value xi, and we can just simplify these particular numbers to produce the value at that particular point. Now, we have said that the interpolating polynomial is unique. Therefore, if you simplify this, it will be same as the Lagrange interpolating polynomial, because we cannot get two polynomials, it is only another form of the Lagrange interpolating polynomial. So, this is another form of the interpolating polynomial. Because that is a unique interpolating polynomial. Therefore, these are the two forms that we have, whereas we found that the Lagrange interpolating is much more difficult, because we need to find all the fundamental polynomials Lix which are of polynomials of degree n. Let us first take an example on this to illustrate how we can apply this formula. Now, construct an interpolating polynomial. Construct the interpolating polynomial. Construct the interpolating polynomial which fits the data x f x is equal to minus 2 15 minus 1 1 0 1 2 19 5 6 31. This example we have considered it in our last lecture, wherein when we defined the Newton's divided differences, we constructed the divided difference table for this particular data. Now, we would like to use that, we can I will just show what we have done last time. This was the example which we had constructed, example 5, wherein we have constructed the divided difference table. Let us just copy these entries here, so that we can apply and get our interpolating polynomial. So, I need to first of all construct the divided difference table for this data. So, let us take this data. So, that is x f x, then we have first divided difference, then we have second divided difference, the third divided difference and the fourth divided difference. So, the data points are minus 2 15 minus 1 1 0 1 2 19 5 6 31. I would give the entries from the last lecture values. So, I would just write down what are the values which we have obtained over here: minus 14 0 9 2 0 4. Then the second divide difference was 7 3 39. Third divide difference was minus 1 and 6, and the fourth divide difference was 1. Now, I would write down our interpolating polynomial as f x is equal to, here we note that this is our x 0, this is our first divide difference with respect to x 0, this is the second divide difference, third divide difference and fourth divided difference. So, these are the 4 divided difference we shall be using with respect to x naught. This will be equal to f at x naught, that is 15, plus x minus x naught, that is x plus 2, into the first divide difference, that is minus 14, that is minus 14. Then we have x minus x naught into x minus x 1, that is x plus 1, into the second divide difference 7, plus x plus 2 into x plus 1 into x minus 0. So, I simply have x, and the third divide difference is 1, and we have x plus 2 x plus 1 into x minus 2 into 1, that is the fourth divided difference. Now, I can simplify this result. Let us write this, simplify this, minus 15 minus 14 x minus 28, and this is 7 into x squared plus 3 x plus 1. Then we have this product, I just have to multiply this by x, that is x cubed plus 3 x square plus x, and we have to multiply this by x minus 2 only, and the result is x to the power of 4 plus 3 x cubed. I am just writing it without simplifying it, so that we can use these values straight away. I just multiplied this by x minus 2. So, this is you have here x to the power of 4 minus plus 3 x 4 plus 2 x square and so on. So, I multiplied by this by and this. Now, we can just collect the coefficients. This is 15, this is minus 28, this is plus 7, there is no constant term here. X square plus 3 x plus 2, is not it? Yes, square. This is equal to 2 x here, correct, that is right, x cube plus 3 x cube plus 3 x square plus minus 2 x cube minus 6, this is okay. So, this is 15 minus 28 plus 14, that is 29 by 28, that is 1. This is minus 14 x plus 21 x, and there is minus 2 x here, and there is here minus 4 x also. So, I would get here plus x, then x square is 7 here, minus 3 here, and you have here plus 2 and minus 4, right. This is, I am writing the coefficient of x squared, that is equal to 7 here, and this is minus 3 here, this is plus 2 here, minus 6 here. So, this becomes 0. So, the coefficient of x squared is 0. So, let us take x cubed coefficient, this is minus 1 here, plus 3 here, minus 2 here. So, this is equal to 0. So, x 4 is only 1. So, I have here this. So, the simplification of this gives us the polynomial as 1 plus x to the power of 4 as a required interpolating polynomial which fits the given data. Now, if I want to interpolate at a particular value, let us say some point 1, let us say f of 1. If I want to find f of 1, either we are substituting it over here and getting it as equal to 3, or alternatively if we do not want to use this interpolating polynomial, and if we just been asked to find what is the value at x is equal to 1, I could straight away substitute in this expression x is equal to 1 and just multiply the numbers. Here we are simplifying, otherwise we could simply multiply the numbers. Now, let us take another example on this. So, I would write construct an interpolating polynomial construct the interpolating polynomial which fits the data x f x minus 2, 9, 0, 1, 1, 6, 457, 586. Now, we note that there are 5 points here. Therefore, if I am using again the Lagrange interpolating polynomial, all the LIX will be, that is your L0, L1, L2, L3, L4, they will be polynomials of degree 4. These are polynomials of degree 4, and we need to simplify the entire thing, but we shall now again use the divided difference, and let us write down the divided differences. X f x minus 2, 9, 0, 1, 1, 6, 457, 586. So, we will have this as first divided difference, that is 1 minus 9 divided by 0 minus 2, that is plus 2, that is equal to minus 4. Then 6 minus 1 by 1, that is simply equal to 5. So, let us put the value as 5. 57 minus 6, that is 51, divided by 4 minus 1, that is 3, that is equal to 17. 86 minus 57, that is 29, divided by 5 minus 4, that is 1, that is equal to 29. Now, let us write down the second divide difference. This is 5 plus 4, that is 9, divided by 1 plus 2, that is equal to 3, that gives us 3. Then corresponding to this, I have 17 minus 5, that is 12, divided by 4 minus 0, that is 4, that is equal to 3. Then I have 29 minus 17, that is equal to 12, divided by 5 minus 4, that is equal to 5 minus 1, that is 4, that is equal to 3. Now, the second divide difference have come out to be all constant and the same. Therefore, the third and higher order differences, divide differences will be 0, 0, and the fourth divide difference will also be 0. Now, this is what I was mentioning last time. If the data given to us is not belonging to the polynomial of very high degree, we would have all the differences of after a certain order will be zeros, so that it will actually give us a polynomial lower degree. Now, we can see that the second divide difference only is non-zero, third divide difference is 0. Therefore, the second divide difference, the coefficient is x minus x naught into x minus x 1. Therefore, this is representing only a quadratic polynomial, all the higher the terms are 0 here. So, let us now construct the interpolating polynomial for this. Therefore, the polynomial will be given by f x is equal to f at x naught, that is 9, x minus x naught, that is equal to x plus 2, into the first divided difference. So, I will now take these values as the values, plus x plus 2 into x minus 0, that is x, into 3, that is the second divide difference, and all third and fourth divide difference are 0. Therefore, it does not give us any particular more terms from here. Therefore, this is simply 9 minus 4 x minus 8 plus 3 x squared plus 6 x, that is equal to 3 x squared plus 2 x plus 1. Therefore, if the given data is representing a lower degree polynomial, that would automatically be reflected in the divide difference table that we are constructing. So, that we would immediately, by looking at the table itself, we shall be able to say what is the degree of the polynomial that is representing this particular data. So far, we have discussed about the case when the data is not equispaced, it is arbitrary data. If you look at this example also, the difference between these two values is 2, this is 1, this is 3, this is equal to 1. Therefore, the spacing between the abscissas was arbitrary. Now, if the spacing between the data points is equal, that is equispaced data, then we can still further simplify the Newton divide difference formula and get a formula which is much more convenient than even the Newton divide difference. As it is, Newton divide difference can also be used for the equispaced data. However, as I said, we can construct still simpler formula than the Newton divide difference. Let us see how we get that one, and for that we shall define some operators and use those operators to derive the formulas. So, let us take the case of equispaced data. So, let us take the mesh spacing as some h. We shall take the mesh spacing as h. That means, we are talking about the points as x naught plus h, x naught plus 2 h, and so on, x naught plus n times h. So, we are talking of the points as x naught, x 1, x 2, x so on. That means, we are talking of the points as x I is x naught plus I h, I is equal to 0, 1, so on n. Now, in order to construct the interpolating polynomials, I would like to define few operators. These are called finite difference operators. So, we call them as finite differences. Now, these operators are very useful for us in solving the ordinary and partial differential equations, wherein we shall use numerical methods, and the numerical methods are based on the finite differences or the finite element methods. So, mostly we shall be using the finite differences. So, let us define three operators. The first operator we shall define is called the shift operator, and we denote this by E. What is the effect of this operator is, if I operate it on any function, it will shift it to the value at the next point. It is a shift operator. So, if I apply E on f x, it will shift it to the value at the next argument, that is x plus h. So, it will go to the shift it to the value at the next point. That is why by definition shift operator. So, it will shift the value of the function at the next nodal point. I can repeat this shift operator once more, E of f x, which I would call this as E square of f x, that will be f of x plus 2 h, that is E of f of x plus 2 h, again it will shift to the next value and so on. Therefore, we define E into E k times operated on f x is e to the power of k f x is equal to f of x plus k h. Here k can take any value. It may be a positive integer, it can be a negative integer, or it can even be a fraction. Therefore, it can be positive or negative integer or a fraction. Now, for example, I can define e to the power of half of f x is f of x plus h by 2. Similarly, I can define e to the power of minus half of f x is f of x minus h by 2. Therefore, any fraction can be taken and we shall define it as f of x plus k h. Now, we have defined the shift operator, which is one of the most important operators that are useful in constructing the many difference formulas in the in interpolation, approximation, in numerical integration and the other area and numerical differentiation also. Let us now define one more operator which is extremely useful for us, and that is known as the forward difference operator. So, let us call this as forward difference operator. We shall give the notation of this delta for the forward difference operator. We define delta operated on f x as f of x plus h minus f of f x. We shall call this as the first forward difference, first forward difference. Now, you can see why this name has been given. This is the difference in the forward direction, the difference between two successive points, that is the value at the next point minus value at the present point, and that we are calling it as the first forward difference. Similarly, we can define higher order forward differences, that is the second forward difference, third forward difference, and so on. Let us see what is the expression for this second forward difference. I write delta of delta f x is delta squared of f x, that will be delta of f of x plus h minus f x. I open it up, delta of x plus h minus delta of f x, but this expression is delta f of x plus 2 h minus f of x plus h, and the second expression is f of x plus h minus f of x, which simplifies to f of x plus 2 h minus twice f of x plus h plus f of x. This is the expression for delta squared f x. The coefficients are 2 c naught minus 2 c 1, 2 c 2. Now, if you proceed further and write down by next difference using this particular values, I can write down delta cubed of f x, the third forward difference. Now, I can let us write straight away from here, operate on this. So, I will have f of x plus 3 h minus f of x plus 2 h, that corresponds to this term, minus 2 times corresponding to this I will have f of x plus 2 h minus f of x plus h, that corresponds to this, and corresponding to this we have f of x plus h minus f of f x. Now, let us simplify. This is f of x plus 3 h, this is minus 1 and minus 2, this is minus 3 f of x plus 2 h, this is plus 2 plus 1, that is plus 3 f of x plus h, and this is minus f x, and this is our third forward difference. This is our third forward difference. Now, you can see the coefficients, this is 3 c naught plus minus sign, change in sign, 3 c 1, 3 c 2 minus 3 c 3. Therefore, these are all the binomial coefficients that come over here as the coefficients of this one. Therefore, if I want any forward difference, say delta k f x I want, I need to construct start with k c naught f x plus k times h, k c naught f x plus k h minus k c 1 f of x plus k minus 1 of h, and so on, and finally, we will have here plus or minus depending on the value of k, in even or odd, this will be plus minus k c k of f x. See, if it is even, you can see they will get a positive sign, this is plus minus plus minus. So, we will have a positive sign when it is even, when it is odd we will end up with a negative sign. Therefore, all the any forward difference can be straight away written by using this the binomial coefficients over here. Let us make it forward difference table. X 0 f 0, x 1 f 1, x 2 f 2, x 3 f 3. Let me take only 4 of them and then illustrate it. So, you will have here first forward difference. This is delta f 0, that is equal to f 1 minus f naught. Now, later on we will fill something, leave some space over here. When we do the next operator, we would like to fill it those gaps. Now, I use these 2 points to get delta f 1, that is f 2 minus f 1. Delta f 2 is equal to f 3 minus f 1. Now, I will write down here my second forward difference. So, I will define here delta squared f naught, that is delta f 1 minus delta f 0. Delta f 1 minus delta f 0, this is second difference. This is delta squared of f 1, that is delta f 2 minus delta f 1. So, this is delta squared f 1 is this minus this. Then I have third forward difference here, and that is delta cubed f naught is equal to delta squared f 1 minus delta squared f naught. Now, let us see how the forward differences are positioned in a difference table, that is delta f naught, delta squared f naught, etc. These values, they are all going on any forward direction. Take any particular value. If you look at, for example, f 1, delta f 1, delta f 1, delta squared f 1, they would all be slanting downwards and they will be having the forward differences in this direction, slanting direction. Okay, we will come back to this, just write down the table. Do it. Now, I would like to define another operator called the backward difference operator. Backward difference operator. For this, I shall use the notation inverted delta. I shall use the notation of invert delta. Definition is, we take the difference in the backward direction, the difference in the backward direction. Therefore, this will be f x minus f of x minus h. So, the current value ordinate minus the ordinate at the previous nodal point f x minus of f of x minus h. So, it is a difference in the backward direction, and therefore, I can now operate it once more. Delta squared f x is equal to, if I operate on the first one, I would get f of x minus f of x minus h minus, I operate now on this, f of x minus 2 h minus f of x minus h. Therefore, f of x, this is minus f x this I have made a mistake here. This is f of x minus h, the current ordinate minus the previous ordinate, minus f x minus h minus f of x minus h minus twice f of x minus h plus f of x minus 2 h. Again you can see that these coefficients are again binomial coefficients 2 C naught minus 2 C 1 plus 2 C 2. Therefore, they would again follow the binomial coefficients only, and therefore, let us write down the next coefficient delta cubed of f x, and then we can generalize it. Let us apply on this. This is with respect to this factor, we will have f of x minus h minus 2 times f of x minus h minus f of x minus 2 h, that is corresponding to this factor. Corresponding to the third factor, we will have f of x minus 2 h minus f of x minus 3 h, which I can simplify and write this f x minus 3 times f of x minus h plus 2 plus 1 plus f of x minus 2 h minus f of x minus 3 h. So, this we shall call it as the third backward difference. This is the third backward difference. Again, this is 3 C naught, this is minus 3 C 1, 3 C 2 minus 3 C 3, which is the same as the binomial coefficients which we had in the forward differences. Therefore, the except in the that we are going in the backward direction, the coefficients are going to the same thing. Therefore, if I am writing a kth backward difference, I will start with k C naught f of x minus k C 1 f of x x minus h plus so on, and lastly I will have here plus or minus k C k f x minus k h. The last one will be f of x minus k h, and I will write it as plus minus of k C h. Now, let us go back to this table and let us fill here the backward difference table, and then I will entry there. Let us write down the backward differences. So, let us take the same 4 values x naught, x 1, x 2, x 2, x 3. So, we have f naught, f 1, f 2, f 3. Now, our backward difference delta we will write it here, first backward difference, that is equal to f 1 minus f naught. Delta f 1 is f 1 minus f naught. Then this will be delta f 2 is f 2 minus f 1. This is f 2 minus f 1 backward difference. This is delta f 3 minus f 2. Now, the second backward difference will be, this will be delta squared f 2 is delta f 2 minus delta f 1. This minus this is delta squared f 2, and this is delta squared f 3, that is equal delta, sorry, this is, we start with that is all right, that is equal to delta f 3 minus delta f 2. And finally, the third backward difference is delta cubed f 3 is delta squared f 3 minus delta squared f 2. Now, why I had written on the same page to illustrate is that given construct a table, I can recognize any element of a column as a possible forward difference or the same as a backward difference also. Now, look at this entry from these two tables, f1 minus f0, this is f1 minus f0. Therefore, the first forward difference can be identified as a backward difference delta f1. If I want to construct a forward difference polynomial or a backward difference polynomial, I can take an element of this here and then recognize it as a suitable forward difference or a backward difference also. This is same as backward difference delta f1, and you can see that this is same as backward difference of delta f2, whereas this was forward difference of f1, and this is also same as backward difference of f3, that is f3 minus f2, oh, this I admit, this is f3 minus s2. So, these are both are same. Similarly, now when I proceed further, now this is nothing but the backward difference with respect to f2, this is the backward difference f3, and this is the backward difference with f3. So, that means I can, if I take a value f3 here, delta f3, delta squared f3, delta cubed f3, and we are going in the upward direction, in the ascending way we are going. So, all the backward differences will ascend, all the forward differences will descend. So, that is how one can recognize in this table this. Any element in this table you can call it either as a forward difference or a suitable backward difference. Therefore, we need not construct separate tables for the forward difference and backward differences, we can identify it from the definition of the forward and the backward differences. Now, even though we have defined the forward, backward and shift operators, all of them are related. We can derive one from the another by the definition. Let us just look at what these relationships are. Relationship between E forward difference and backward difference. Now, let us write down what is our definition of delta f x, that is f of x plus h minus f of x. Therefore, this is equal to E of f x minus f x. By definition, E of f of x plus h is E of f x minus f of x, that is equal to E minus 1 of f x. Therefore, the operator delta is equivalent to the operator E minus 1, or alternatively E is equal to 1 plus delta. I can bring minus 1 to this side and I can have this as the relationship between this. Now, you would see that getting the higher order difference is very simple for us here. If I want delta k here f x, it will be operating E minus 1 operate on E minus 1 so on k times. So, this will be E minus 1 to the power of k f x. So, E minus 1 to the power minus 1 to the power of k. Now, you see if you write the binomial expansion symbolically, this is nothing but you are going to get all your binomial coefficients. So, this will be simply e to the power of k minus k c 1 e to the power of k minus 1 and so on operate on f x. So, whatever we have derived earlier, those binomial coefficients would automatically turn up, and I can view the forward differences that were written there by using this particular way also. Now, let us write down what is our backward difference, that is f of x minus f of x minus h, that is f x minus e to the power of minus 1 of f x. So, we said k can be positive or negative or a fraction. So, I will take k as minus 1. So, e to the power of minus 1 of f x will be f of x minus h. Therefore, this is 1 minus e to the power of, I will take e to the power of minus 1 as inverse operator, e to the power of minus 1 f of x. Therefore, our delta is 1 minus e to the power of minus 1. now I can bring it to this side, E minus 1 is 1 minus delta, I bring it to this side and this, and invert it again, E is equal to 1 minus delta to the power of minus 1. So, if I want delta in terms of E, I will use this, if I want E in terms of backward delta, I will use this particular expression. Now, all the backward differences, as I mentioned in the case of the forward difference, I can get from here also. This will be simply delta to the power of k of f x will be simply 1 minus e to the power of minus 1 to the power of k of f x. So, I can now open it up in a symbolic way by using the binomial expansion, and I can operate it on f x and get all the forward difference. Therefore, again they are again binomial coefficients, as you can see here. These operators are all interlinked. Therefore, that was the reason why we were able to recognize in the difference table a particular element as either a forward difference of a particular value or a backward difference with respect to another backward value. Now, one more important operator that we would like to have is called the central difference operator. The notation used for this is this delta. Now, it is a central difference, therefore, it is a symmetric difference. So, if I operate on f x, what it does is it takes the value at the half the next point minus f x minus half. This is symmetrically placed about the x point that we are taking. This is our x and this is your x plus h by 2 and this is your x minus h by 2. So, it is symmetrically placed. However, the interesting thing note is that these x plus h by 2, x minus h by 2, they are not the nodal points, because we have got x 0, x 1, x 2, x 3, x 4, but x 0 plus h by 2 is not a nodal point. Therefore, this difference is not using the nodal point, but if I now go to the next difference, this will be delta of f x plus h by 2 minus delta of f x minus h by 2. So, if I now apply on this, it will take the next value as f x minus f of, okay, I will write one more step this. This is delta of f x. Now, operate on this, this will become f of x plus h by 2 plus h by 2, that is x plus h, f of x plus h by 2 minus h by 2, that is f of x, minus x minus h by 2 plus h by 2, that is x, minus f of x minus h by 2 minus h by 2. So, that is x minus h. So, this is f of x plus h minus twice of f x plus f of x minus h. All these three are nodal points and now they are symmetrically placed. Now, we are using these ones. Now, there is a big advantage which we shall see a moment later, as the central difference operators would be much more accurate than the other differences, the forward or backward differences. We will define what we mean by better approximations. Because they are symmetrically placed, the error in this case is smaller than in the forward and backward differences. Now, I can therefore construct a central difference table also for this. Let us just write down few points: x 0, x 1, x 2, x 3, f 0, f 1, f 2, f 3. What I would write here is, I will take delta f half, that is equal to, by definition, f 1 minus f 0. Now, if I write delta f half, that is x 0 plus h by 2, then it will be f x 0 plus h minus f x 0. So, this will be f 1 minus f 0, then this will be delta f 3 by 2, that will be, that is 3 h by 2 plus h by 2, that is f 2, 3 by 3 h by 2 minus h by 2, that is f 1, that is f 2 minus f 1, and this is delta f 5 by 2, that is f 3 minus f 2. But these two combination will give us delta squared of f 1, because that is from this definition that we have, that is delta squared f x will be f x plus h minus 2 f x plus f x minus h. Therefore, delta squared f 1 will be f 2 minus 2 f 1 plus f naught, that is equal to delta f 3 by 2 minus delta f half, and which we can write this as f 2 minus 2 f 1 plus f naught. Now, this is also I can write down delta squared f 2, this minus this, delta f 5 by 2 delta f 3 by 2, which would be equal to f 3 minus 2 f 2 plus f 1. Then using these two I would get delta f of 3 by 2, that is 1 plus h by 2, that is x 1 plus h by 2 is x this. These odd differences would not be using the nodal points, because this is all half distances f, the here the way in which we have written has f of, they are using these differences all of them, but we have written it as delta f half delta f 3 by 2 and that. Therefore, we have now constructed the table such that all of them belong to the data points only, but these are as taken as the central difference of delta half. Now, we will just close in a minute. Let us see what is the relationship between delta and E. So, if I write this delta f x, I can write this as e to the power of half f x minus e to the power of minus half of f x, x plus h by 2 x minus h by 2. So, this is to the power of minus half, and this, that is e to the power of half minus e to the power of minus half of f x. Now, we want to put this in a notation. If you remember, sine hyperbolic of x is e to the power of x minus e to the power of minus x by 2, right. This expression shall be used when we get the equivalence of the delta operator with the differential operator d is equal to d by dx. Therefore, our equivalence here is e to the power of half minus e to the power of minus half, which if you want to take e to the power of half, I mean, so that you can recognize these operations that we have written it here, we can write this also as e to the power of half into 1 minus e. I take e to the power of half common. So, this will be 1 e to the power of minus 1, or I can take e to the power of minus half outside and write this as e minus 1. Multiply it out, this is e to the power of plus half minus e to the power of minus half, and this is e to the power of half e to the power of. So, whichever way you want to look at it, I can write this operator in terms of this form and then use that particular thing. Okay, we will stop at this today.